If theta is 0, that drops out, and this becomes 1. So you're at this point right here. So the arc between these 2 points is just the height of the function. So let me just darken this in. That's what this is right here. And notice that's everywhere on or below f of u. Therefore, this function, and this is going to be true for any two functions, for this bell-shaped curve. The height of the function has to be everywhere on or above this height as you go from u to v. So in other words, what can't happen is something like this. If the function looked like this, that wouldn't do. Because here's f of v, here's f of u, and in this interval right here, you're going below f of u. So it can't dip like that, and for it to be quasi-concave. Now, this is a quasi-concave function. If you pick any 2 points on this function, on this bell-shaped curve, that equation is going to hold. Now, what would a concave function look like? This is quasi-concave. In fact, if this is an inequality there, then it's strictly quasi-concave. In fact, this one is strictly quasi-concave. Okay, because there are no flat portions of the curve. So this equation holds. So this is strictly quasi-concave. Jacob, did you want to say something? Now, what would a strictly concave function look like? What would its shape be? And how would it differ from this? Well, the strictly concave, yeah. Ian, did you want to say? Could be, yeah, a straight line would be concave. Also, a curve like this. I mean, I'm thinking of something similar to this. This shape right here. Upside down U. That would be strictly concave. Right, Ian?
I was trying to say that, but I didn't.
Oh, okay.
Upside down U.
Okay.
It's like a really simple way of saying it.
Okay, yes, okay, yes. Because for it to be strictly concave, what is the algebraic condition for strict concavity? Now, I know we talked about this. It may have been a week or two ago, though. What is the condition for strict concavity of the function? Algebraically.
That it always be?
Cody?
I know we drew that line. It had to be
Yes.
below the curve.
Yes, exactly. If you pick any 2 points, u and v now, let me pick any 2 points, u and v, and connect them with a straight line. The straight line has to lie everywhere strictly below the height of the function, except at the points themselves, of course. Okay. Theta is restricted to be between 0 and 1, so you can't be at either 0 or 1. But everywhere you see this line lies below the curve. Now, what differentiates these two and makes this would of course, this would also be strictly quasi-concave. That's a weaker condition. See, for quasi-concavity, all you need for this is for these values to be greater than the lower value, f of u. F of v looks like it's a little bit higher. So this is certainly strictly quasi-concave, but it's also strictly concave. Okay. Quasi-concavity would allow for this shape to have like a bell shape. Notice in this case right here, it wouldn't be strictly. Why wouldn't this curve right here be strictly concave? The one on the left.
Because if we extended u to the left and we connected to any 2 points, well, one of them being to the left of u, we would actually not be in our region. We would pop out of the function of bell curve, right?
Okay. Let me see. Suppose we pick this point. U prime, V prime. Right here. Now, what would be the problem in trying to argue that this function is strictly concave?
Line you connect there is above the function.
Yes, right. Between these 2 points, if you connect them with a straight line, the straight line lies above. This segment right here is convex rather than concave. But nevertheless, this function is strictly quasi-concave. It's not concave, okay? But it is strictly quasi-concave. So quasi-concavity is a weaker condition than concavity, okay? Any bell-shaped curve would be quasi-concave, but wouldn't be concave. Okay, it's a weaker condition. Also, what about straight lines? Suppose you have a straight line. What can you say about that? Is this quasi-concave?
Yeah.
Yes, because here, let this be V, this be U. Notice we have f of V is greater than f of u. And every point on this function is greater than or equal to f of u. So this is strictly quasi-concave, as well as being quasi-convex. Quasi-convexity, all you have to do is you take this and you change this to a less than or equal. Then that's the condition for the function to be quasi-convex. Okay. A quasi-convex function would be an upside-down bell-shaped curve. Let's look at an upside-down bell-shaped curve. X. Say it looks like this. Now, pick any 2 points, U and V. Oh, here's U, here's V. I just want to make sure the height of the function is higher at V. So now, here's f of V. Here's f of U. So f of V is greater than or equal to f of U. And that means now the function, the height of the function between these 2 points has to be everywhere below, oh, actually I said the wrong thing here. This should be f of V here, not f of U. Excuse me. When you switch to quasi-convexity, this should be the higher point instead of the lower. But you see, each of these values is less than or equal to this point up here. Okay. So that's the condition for quasi-convexity. So this one is quasi-convexity. I'm having a little trouble spelling quasi here. There we go. Okay. Now you have to be lower than the higher value. Then it's quasi-convex. Think of it upside down bell shape. This function over here is also f of v greater than f of u. And this is also always less than or equal to the highest value. So this is both quasi-concave and quasi-convex. It's both concave and convex too. So it's all. But it's kind of important to remember, any linear function is quasi-concave and quasi-convex. Because a lot of times our constraints in economics are linear functions. So in our problem that we did, both of our constraints were linear functions, so they're both quasi-convex. Our objective function was quasi-concave. Therefore, we could use the Arrow-Thoven sufficiency theorem to guarantee that we have a global maximum at the point that satisfies the Kuhn-Tucker conditions. Okay. Okay. This stuff on quasi-concavity I know is a little difficult. So what I'd like you to do over the weekend and definitely before Wednesday, our review session, reread pages 364 to 371 in the textbook where they talk about quasi-concavity, which is, again, a weaker condition than concavity. And this idea of quasi-concavity is so important in economics. We assume that the utility function is quasi-concave. In other words, diminishing marginal rate of substitution, convex indifference curves. Therefore, this tangency point between the indifference curves and the budget line gives us the maximum utility. Okay, so it is an important concept in economics. I know mathematically it's kind of tricky to master, but spend some time on quasi-concavity between now and Wednesday. Okay. There is just one more very quick thing I need to go over, and that is the envelope theorem. The envelope theorem is relatively straightforward and easy to explain. And let me discuss it in the context of the Lagrange function. Okay. You recall that I told you that the Lagrange multiplier has the interpretation of being the change in the optimal value of your objective function for a 1 unit increase in C. If the constraint is income, the Lagrange multiplier is the marginal utility of income. Let me just discuss this more formally. Look at this Lagrange function here. You want to maximize f of, let's say, x and y, two variables, x and y, subject to the constraint. Let's write it as an equality constraint, that g of xy is equal to c. And we're going to assume that this constraint is exactly binding. Okay. And let's not worry about the inequality, the non-negativity conditions. Okay, let's not worry about that. Then what is our Lagrange function here? What's our Lagrange function for this maximization problem?
F of xy.
Right, f of xy.
Plus n.
Right,
C minus g of x.
right, exactly. And I told you that the interpretation of lambda, actually lambda star, the optimal value of lambda when you satisfy the first order conditions, is just this. The derivative of f star, the optimal value of f with respect to a constant. That is what the interpretation of lambda star is. But now let me just prove that. Z, your Lagrange variable Z, is really a function of what variables? What are the three variables? X, y, and lambda. So let me just emphasize that. And we think of C here as being what? C in mathematical language would be a what? A constant, but it would also be, it's an unspecified constant. So it'd be, what's an unspecified constant? What's the term for that? Parameter. Parameter. It's just a parameter. So let's do this. X, y, and lambda, we understand, are the variables. But let's write a semicolon there and put C next. So let's consider the possibility that C might change. Okay? So really, you can kind of think of C as it's being a variable too now, if we're allowing its value to change. But we're optimizing on X, Y, and lambda. Okay. So what are our first order conditions? Our first order conditions are that partial Z, partial X equals 0, partial Z, partial Y equals 0, partial Z, partial lambda equals 0. Okay. Those are the things we're optimizing on. Okay. Now, what is the total derivative of Z with respect to, well, let's do it in two different parts. I want to get the total derivative of Z with respect to C. But let's just first get the total differential. What is dz going to be? Think of Z as being a function now of X, Y, lambda, and C. Think of C as being another variable, even though we know it's really a parameter, but we're going to allow its value to change. So consider C to be a variable. What is the total differential of Z then, if we allow C to change? Well, Z is a function of these four variables, so the total differential must be this. It must be partial Z, partial X dx, plus partial Z, partial Y dy, plus partial Z, partial lambda d lambda, plus partial Z, partial C dc. Because now we're thinking that Z depends on four things: X, Y, lambda, and C. So the total differential has to be this. Total change in Z must be the change in Z due to the change in X, plus the change in Z due to the change in Y, plus the change in Z due to the change in lambda, plus the change in Z due to the change in C. Now, let's get the total derivative of Z with respect to C. Just divide both sides of this equation by dc. And then we get the following. And dc divided by dc is just 1. Okay? So this is the total derivative of Z with respect to the constant. Okay? And when the constant changes, say when income changes, X is going to change. So X will be a function of C. When the constant changes, Y is going to change. When the constant changes, lambda is going to change. And then this will be the direct effect. Okay. Now, if we're always optimizing, if this individual is always maximizing their utility, what is partial Z, partial X? Okay, well, in this case, go back a chapter. In this case, let's assume this constraint is exactly binding. So in that case, partial z partial x is what? 0. So that's 0. What about partial z partial y? That's 0. That's just the first order conditions. So we're assuming all the constraints are binding. Partial z partial lambda, 0. So all of these terms drop out. Then what is the total derivative of z with respect to the constant c? It's just the partial derivative of z with respect to c, holding x, y, and lambda constant. It's just the partial derivative. The total derivative and the partial derivative are the same, because if you satisfy the first order conditions, this drops out, that drops out, that drops out. That means, what is partial z partial c here? Just look at this equation right here. What is partial z partial c? Lambda. The coefficient on lambda is just c. So lambda is the coefficient on c. So it's just lambda. Or more in particular, since we're using the optimal values of x, y, and lambda, it's lambda star. So what this shows you is the rate of change of z with respect to the constant. The change in the constant is just lambda star. Now, if the constraint is exactly binding, then this term drops out too. And then the change in z is the change in f. So you get this result. The derivative of the optimal value of your objective function with respect to the constant is just lambda star. Okay. That is really using the envelope theorem. The envelope theorem says the total derivative in an optimization problem is just going to be the same as the partial derivative, because all these terms, like this, all these terms drop out. So the total derivative will just be the partial derivative. So this will make it a lot easier to get these derivatives. And you can use this envelope theorem whenever whenever you're maximizing or minimizing the value of the objective function. You can utilize the envelope theorem. Okay. Let me give you another simple example. Okay. So in this case, if C is income, then lambda star and F is utility, then lambda star would just be the marginal utility of income. So I'm justifying that statement I earlier gave you about lambda star. I'm deriving it mathematically. Let me give you an even simpler example. Suppose you have something like this. Y equals f of x. And x is your independent variable, y is your dependent variable. You want to maximize this, but there's some parameter a. And now you want to know, you want to get this, say, total differential of y. Total differential of y is just partial f partial x dx plus partial f partial a dA.